Sir, good evening.
Hi, good evening, everyone. Good evening. So let's get started. Okay. So in the yesterday's lecture, we looked at um, the RK4 method was done. So we looked at the solution to system of ODEs, right? I think we finished the solution to system of ODEs. We have looked at how stiffness plays a role when you have multiple, ODEs, and how these stiff systems naturally occur in chemical reactions between different species, and then when you have vibration of a complex system with several springs and other elements and so on. And we also looked at implicit methods using which we can linearize and then solve these stiff systems by taking larger delta t wherever it is not required, and then by taking smaller delta t wherever it is required. Okay, so basically we're talking about some kind of an adaptive time stepping kind of thing. Okay, so with that being done, let us look at so far we have been only looking at solution to initial value problems, right? Or IVPs is what we have been looking at so far. That means where the conditions are specified at one end of the domain, right? So let us look at the boundary value problems. Okay. So boundary value problems arise when you specify the conditions or let me put it this way. Okay, so let me say you have a differential equation. Okay, let us call it y double prime equals some f of x comma y prime. Okay, now one thing you see already here is that the moment we went to boundary value problems, I have written a second derivative, right? Because boundary value problems require that the ODE to be at least second order accurate, right? At least second order degree. Because we are specifying two conditions, right? So if I were to specify, let us say if we want to solve this second order ODE to using as an initial value problem. So if it is an initial value problem, we will have specified y of 0, y prime of 0, right? These two values. That means we are specifying both at t equal to 0. Then this is basically is an initial value problem, right? Whereas in a boundary value problem, the conditions are some conditions are specified at one end, and the remaining conditions are specified at the other end. Okay, that means if we're going to specify few conditions at t equal to 0, and then we're going to specify, or if this is, let us say, x, if this is, let us say, x, then if we specify at x equal to 0 some conditions, and then at x equals L, if we specify the remaining conditions, then such a problem is known as a boundary value problem. That means we are specifying these values at both the boundaries, right? Some of them at x equal to 0, some of them at x equal to L. Again, these kind of ODEs are very much possible in science and engineering. So then that means, what does it mean? That means we're going to specify, let us say we're going to specify y of 0, and then we're going to specify y of L. Let us say we can say that y of 0 is specified as y0, y of 0 is specified as y sub 0. Similarly, y at x equals L is specified as y sub L. Okay, so instead of giving y0 and y0 prime, that is both the function value and the derivative at t equal to 0 or at x equal to 0. If I were to write, right, at specifying at x equal to 0, right, we are specifying value of y itself, not the derivative, at y at x equal to 0 and x equal to L. I mean, we are specifying two values, but we are specifying both of them for y itself, but then we are specifying them at two different ends. Okay, so this is basically a boundary value problem. Okay, now these kind of boundary value problems can be solved using a couple of different approaches. The first one is known as the shooting method. Okay, in the shooting method, what we do is that we're going to apply the solution methods of initial value problems to solve boundary value problems, such as the RK2, RK4, etc. Can be used to solve the boundary value problem. Okay, so that is the what is known as the shooting method. Whereas in the direct method, what we do is that essentially this is basically a straightforward finite difference approximation of the ordinary differential equation. Okay, so of the ordinary differential equation, and once you have the straightforward finite difference approximation of the ODE, then the regular solution techniques can be used to solve for this problem. Okay, to solve for the obtained linear algebraic equation. Solution techniques can be used to solve the resulting system of linear equations. Okay, so these are the two methods that we're going to learn in the context of boundary value problems. Okay, so let us first look at the shooting method, and then we'll come back to the direct method. Okay, so let us look at the shooting method. Okay, so what do we do in the shooting method? So let me again take this example that we have y double prime equals some function of x comma y prime. Okay, and then we realize that for a boundary value problem, the minimum, at least we should have a second order ODE. Okay, then only we can apply boundary value problem. Otherwise, if we have just one, you cannot distinguish between a boundary value problem and an initial value problem. Okay, let us say out of this we are also given what is y at 0 is given as y sub 0, y at x equals L is given as y sub L. Okay, these two are given, which is basically makes them qualified as a boundary value problem. Now let me use some variable transformation. I'm going to call my u equals y, and I'm going to call v equals y prime. Okay, I'm going to denote my y using a variable u and then y prime using variable v. Then we already have u prime equals v. Okay, that is one of the equations. Then the other equation is I can go back and then substitute into this equation. So y double prime will basically come out to be v prime, right? Because v defined as y prime. So v prime is going to be y double prime, would be a function of x comma y prime, but then y is we have denoted as u, y prime we denoted as v. Okay, so essentially we have two equations. The first one is u prime equals v. The other one is v prime equals some function of x, u, and v. Okay. So what we did was we converted, just like what we have been doing till now. We converted this second order ordinary differential equations into two first order ordinary differential equations, right? That's what we have done. Okay. So we have, of course, transformed the governing equation into two first order ODEs, but then we should also, to be able to solve, we should also transform these boundary conditions. So boundary conditions are given as y at x equal to 0, because my y is same as u. We can write one boundary condition as u at x equals 0 equals y sub 0. That is what is given. The second boundary condition is given as u at x equals L equals y sub L. Okay. So now you can clearly see we want to solve for u prime equals v and then v prime equals f of x u v. But then we are given two conditions on u itself and then no conditions for v. Right? So no conditions for v are given, whereas two conditions are given for u. Okay. No conditions are given for v. But ideally, we would have liked if we are given one condition each for each of u and v, rather than two conditions for u and none for v. Okay, so we don't like this. Rather what we would have liked is we would have given u of 0 equals some y0 or something. We would have liked if we are given what is v of 0 equals some v0, right? Then what we have done is we would have gone back and then we know what is u at x equal to 0, v at x equal to 0. We would have started our initial value problem, that is RK4, RK2, and we would have just solved everything. Okay. Unfortunately, that is not the case because this is not an initial value problem. This is a boundary value problem. Okay. But then what we do in this case is that to make our to basically make our initial value problem solution methodology, that is RK4, RK2, trapezoidal, all these things, to make them work for boundary value problem, what we do is that we start with u of 0 equals some y0, and because we are not given v of 0, we will still make v of 0 equal to some v0. So we basically make a guess for v of 0. Okay, so it means I'm going to basically make a guess for v of 0. Okay, and then with that guess, I'm going to apply my standard techniques such as, let us say, RK2, RK4, etc. And then I'm going to solve for u and v. That means I want to solve for what is u of x. I'm going to solve for what is v of x. Okay. So once I solve, I would know what is u as a function of the entire x. That means I'm going to obtain u as a function of going from x equal to 0 to all the way to x equal to L. Similarly, I'm going to obtain v as a function of x equal to 0 to L. Okay. So I have the entire distribution. But then we know that once I have reached here, I know the values of what are u at L and v at L, right? That means think of it like some x equal to 0 and then some x equals L, and then I'm able to integrate and then solve for, let's say that is my u, and then this is my v. Okay, so this is my v and this is my u. Okay, so I'm able to solve this using, but then as you recall, I have made a guess for v. So this v0 I have guessed, whereas this u0 is given. Okay, so this is the guess value. So what will happen is that now with this I have calculated all these things, but then we know that because it's a guess value, of course the solution will not be correct, but then we are given what is u at x equal to L, that is given as y of L. So I'm going to compare the u of L I have obtained with the given YL, right? And these two in general would not match unless we are very lucky. These two are not going to match. That means because they are not going to match, the guess we made for V0 is not correct. Okay, so we're going to go back and then make V0. We're going to basically make another guess again, and then solve all the way for u and v. And then once you obtain what is U of L and V of L, you compare that U of L to YL. If that is not again matching, you go back and make another guess and so on. Okay. So that is the iterative process. That is the iterative process that we will use to make the standard algorithms for initial value problems to work for a boundary value problem. Okay, so that means this is how we can make our existing code to work for boundary value problem. In one way, you can think of it like this: you have already written a code for solving initial value problem, and you don't want to write another code. You just want to make use of the same code because it is, let us say, fourth order accurate, it has many benefits and so on. So you just want to apply the same code to boundary value problem. Okay, that is how the thought process here has resulted in this particular method known as shooting method. But then of course, as you can see, we don't want to randomly guess and then find it because there is no limit, right? I mean, you can keep guessing, and then there should be one particular way in which this guess value will be guided such that we converge to, such that U of L will converge to the value of YL in as many less number of iterations as possible. Okay, so that is the idea here. So it turns out if you have linear problems, okay, that means if the function on the right hand side x, y, y double prime is linear, okay, if it is linear, then we just need 2 steps or 2 iterations, and then we will be able to solve for the solution in just 2 iterations. Okay, we don't need anything more than 2 iterations. Whereas if it is nonlinear problems, that means your f x, y, y prime is nonlinear, then you need to perform several iterations. Okay, then several iterations are required before you can converge on a problem. Okay, that means we will do several iterations, and then approximately when y of L when U of L becomes close to YL, we're going to stop the iterations. Okay, fine. All right. So that is the idea here. Any questions so far from anybody? Okay, no questions. So let me proceed. So now I'll go back and then apply. Go back to the general. We'll look at a general second order ordinary differential equation. So let me write a general second order ODE. Okay, let me write this as some y double prime x plus some coefficient a of x times y prime x plus some coefficient b of x times y of x equals f of x. Okay, so this is still a linear second order ODE. This is still linear because we are only multiplying with a of x and b of x, not with a of y or b of y, right? We are not multiplying the unknown with itself, or we are not multiplying the derivative of the unknown with itself or something. Okay, so as a result, this is still a linear second order ODE because we are only depending on a of x and b of x, which are still known values. Okay, it's some x square plus cube and so on. So that's why this is still a linear problem. Yeah. So because it's a linear problem, as we discussed, we just need only 2 steps or 2 iterations to solve for the final, to solve for this thing. Okay, that means let me say now we are given 2 conditions, right? One condition was y of 0. The other condition was y of L, right? We are given these 2 boundary conditions on y. Okay, let me say we want to solve this using 2 values. Let us say we want to solve with y of 0. Okay, so let me say we have made 2 guess values. Y of 0 is given. Okay, so we are given y of 0 and y of L. So this is basically nothing but y of 0 equals y0. And then, oops, y of 0 equals y0, and then this is equals y sub l. Okay, that is what is we are given. Okay, now I want to start with, let us say I make two guess values. I want to take y1 of 0 and then y2 of 0. Okay, but then we take y1 of 0 because it is given as equal to y0, and then y2 of 0 equal to y0. But then to solve for this using my ODE, I also need a condition, that is y1 prime of 0, which I'm guessing. So I'll press this as y1 prime 0, and then y2 prime 0, I'm going to guess it as y2 prime 0. Okay, now what is given to me is this is given, but these are not given. So these are the guess values I have made, and then solve the problem, right? And then of course this is given to me, but I have not made use of this till now, which I'm going to make use of. So I'm starting with y1 and y1 prime, that is one guess, and I'm going to integrate and obtain what is y of x, right? I just need two problems. So, and both are specified at x equal to 0, so I can apply my initial value problem and solve for y of x. Similarly, I'm going to use y2 of 0, and then with y2 prime equal to 0, which is another guess value, okay, and then I'm going to solve for y of x. So this is going to be y2 of x, this is going to be y1 of x. Okay, I have obtained some solution. Okay, let us say y1 of x is something like that, and then y2 of x is something like this. Okay, so this is my y2 of x, this is my y1 of x. Okay, I have solved with these conditions, with basically this is the guess values I have used. Okay, now of course again this y1 of L and this y2 of L do not match this y of L at, right? Because we are not so lucky. Okay, so it's not going to match. But of course I have taken the correct y0 value. That means this y0 is the same as this y0, which is the specified condition at x equal to 0. Okay, so I have now done this thing. Okay, but then we know that the given problem is linear, right? So linear superposition will work, right, between the solutions. That means if I have a solution y1 of x and y2 of x, I can also say that y of x, any other solution, can be obtained by linear combination of y1 of x and y2 of x. So I can say c1 times y1 of x plus c2 times y2 of x, which will give me y of x, is also a solution to the problem. Okay, provided my c1 plus c2 sum to 1, right? We can have 50% of this and 50% of that, or 30% of this and 70% of that, and so on. So okay, and then we know that this is basically also will be a solution because the given problem is linear. Okay, so if this is the case, I can also calculate what is y at x equal to L, that is given specified as yL equals c1 times y1 of L plus c2 times y2 of L, right? This is given as c2 times y2 of L. Okay, now we realize that y1 of L we already know, y2 of L we already know, because we have with the guessed values of y1 prime 0 and then y2 prime 0, we have integrated and obtained what is y as a function of x. So I know what is y1 as a function of L. This is numerically obtained, and y2 as a function of L. So I know these two values, and I know this value. That means I know everything here except for C1, C2. But then what you see is that now for C1, C2, I have one equation here. This is the second equation. So I have now two equations and two unknowns. I can solve for C1 and C2. That means I'm going to basically solve for C1 and C2 from these two equations, in which I'm actually enforcing the other boundary condition that is given to me, that is y at x equal to 0, I'm enforcing here to obtain what is C1, C2, the relation between C1, C2. Okay. Now the relation between C1, C2 will change depending on how your y1 of L and y2 of L are obtained. So if you have made a different guess, your C1, C2 will be different because you still have to take a linear combination of them and then calculate yL. Okay. So that is the idea here. That means once I have C1, C2 from this calculation, I can go back and plug in C1, C2 in this equation and calculate y of x. Now that y of x will be the correct solution that is going to satisfy both y at x equal to 0, which is given as y0, and then y at x equal to L, which is given as yL. Okay. So let me calculate this. So I can write my C2 equals 1 minus C1, and then yL equals C1 y1 of L plus 1 minus C1 y2 of L. Okay, so I can write this as y2 minus y2 of L, sorry, yL YL, this is YL, Y sub L, equal to C1 times Y1 of L, plus, sorry, this is going to be again minus Y2 of L, okay? So that's what I have, okay? That means I can write my C1 here as Y sub L minus Y2 of L divided by, I think my YL is not looking nice, okay, YL divided by Y1 of L minus Y2 of L, okay? So that is my C1. Similarly, I can calculate what is C2. C2 equals 1 minus C1. So I can write this as 1 minus Y of L minus Y2 of L divided by Y1 of L minus Y2 of L. That's going to get Y1 of L minus Y2 of L minus YL plus Y2L divided by Y1 of L minus Y2 of L. Okay. Now minus Y2L plus Y2L gets cancelled. So my C2 is equal to Y1 of L minus Y sub L divided by Y1 of L minus Y2L. Okay. So I have now both my C1, C2 values. C1 was Y of L minus Y2 of L divided by Y1 of L minus Y2 of L. Okay. And C2 is Y1 of L minus YL by Y1 L minus Y2L. So I'm able to obtain C1, C2 purely from YL, that is the given boundary condition, and from Y2L, that is what I have obtained with some initial guess for Y0 and Y2 prime 0, and then from Y1L, which is basically obtained at x equal to L for Y1, which was solved using Y1 of 0 and Y1 prime of 0. Okay. So with all this, I'm able to calculate what is C1, C2. Now that I know what is C1, C2. Now I know what is C1, C2, and I also know what is Y1 of X and Y2 of X. I can construct my solution Y of X equals simply by multiplying C1 with Y1 of X and plus C2 times Y2 of X. That's all, right? Now with this is my solution. As you can see, we have only 2 steps, right? Or 2 iterations. In fact, we didn't even iterate, right? We just basically did 2 independent solutions saying Y1 of 0 and Y1 prime of 0, Y2 of 0 and then Y2 prime of 0, right? These are essentially 2 independent guesses. With 2 independent guesses, we are able to obtain what is the answer. And we were able to do this only because the problem was linear, okay? Fine. Is it clear, this part, before we move to the nonlinear part? I think this needs to be clear. Okay, any questions, clarifications on this from anybody?
So, can you please share us where this can be used, like some examples kind of a thing?
Yeah, sure. So essentially, for example, you have, let us say, a boundary, a boundary layer problem. Okay, let us say you have a flow over a flat plate or something where there is some boundary layer that is developing. Typically, you'll have, a profile something like this. Okay, and then you know that essentially U is 0 at x equal to 0. And then you will also know that U tends to U infinity at x goes to a very large value. Okay, x goes to some, I'm writing here infinity, but let's say this is some 20 or 30, whatever, very large value in terms of the domain that you're considering. So you are given basically 2 conditions. U at x equal to 0 is 0. U at x equal to some distance far away, let us say this is some y that is very far away, equals U infinity. Okay, so basically you're given 2 conditions on U, and you want to calculate what is this profile, how does the velocity profile look like in flow over a flat plate or flow over a cylinder or anything like that, in any of these things. So if that is the case, essentially you will use, so this is basically like a boundary value problem. Okay, then what you do is that you can apply shooting method, for which you have already written the code to solve for this thing. Okay, of course, in the context of fluid flow equations, this will not come out to be linear. Okay, this will still come out to be nonlinear. So as a result, the method I have just described you cannot use directly because it is nonlinear. But you can use a variant of this thing, the nonlinear version of it, which I'm going to discuss in a little while. Okay, but these kind of problems are always there. Even if you take a beam or something, you will specify things at both ends, right? You know, you will specify that at the one end of the beam, this is the value; at the other end of the beam, this is the value, and then how does it vary in between? Okay, that is the idea. Okay, so I think these kind of problems are, we come across often.
Okay, sure. Thank you,
Yeah.
sir. Thank you.
Yeah. Anything on the method, anybody? Okay, if no questions, you can feel free to stop me any point. Okay, so let us look at then what will happen in the context of a nonlinear right-hand side. Okay, when we have a nonlinear function f, which is x of y comma y prime. Okay, so when you have nonlinear function, what will happen? Then what will happen is that the relation, so this is basically nonlinear. That means the dependence of, so what we have done is we have this y prime 0, which we're using to calculate y of L, right? We are essentially doing some guess value and then getting y of L. So till now, this y prime L to YL is basically a linear variation, right? When you use y prime 0 and then integrate, you are essentially doing some kind of a linear problem. But then this dependency will become nonlinear, because you are going to use this equation to solve for what is y of x, right? So as a result, y of x will be nonlinear because you are going to use this particular f of x y prime, which itself is nonlinear. Okay, so that is what we should look at. That means if I were to think about y prime 0 as my independent quantity, right? I'm going to think of this as independent quantity because I'm going to guess what is y prime 0. Okay, so we are given y is 0 as boundary condition. The other condition is given as YL, right? We are given YL as the other condition, but then we're going to make a guess for y prime 0. So that's why, because we are making a guess for y prime 0, I'm going to think this as independent quantity, and I'm going to look at what is the dependence of y prime 0 on YL. Okay, so this is basically the dependent quantity. Okay, and this is the independent quantity. Okay, if this is the case, I'm going to make I'm going to draw some kind of a function here. Okay, so this function I'm going to choose on the x-axis y prime 0. On the y-axis, let me choose y of L. Okay, so we made y of 0 is given, y prime 0 is guess value. With that, we have integrated, obtained some YL. Okay, that is the idea. So this is on the x-axis is your independent quantity. On the y-axis is your dependent quantity. Okay, and we also know that this relation between y prime 0 and YL is governed by some nonlinear function. Okay, let us say our nonlinear function looks something like that. Okay, so this is the nonlinear function, which is your f of x, y prime or something. Okay, then what I did was I made two guesses, right? I make a guess, right? I make a guess here. So this is my y1 prime of 0. But I'm already given what is y of 0. Okay, so I'm making one guess, y1 prime of 0. And with that guess, I'm integrating and calculating what is y of x, right? With the guess of y1 prime 0, I'm integrating with y0 and y1 prime of 0, calculating what is y of x. Then I know what is also y at x equal to L. That means this is going to be my y1 of L, right? Because if you know the entire y of x, I know what is y1 of L. Then I'm also making another guess, that is my y2 prime of 0. So I'm making another guess and then calculating y2 of x, which is going to give me basically y2 at L. Okay. So far it is the same as what we have done before. Only thing was, in the context of a linear problem, right? We made these two guesses, and we knew that this variation between, the functional variation between this and this was linear, right? That's why we were able to essentially put in any, whatever we got, we were able to calculate what is the root here by taking C1 times y1L and C2 times y2L and then calculate. Okay, but then now we realize that it is not linear, so it is not this red line that we have, rather it is a blue line. Okay, it is the blue line. So we won't be able to directly calculate unless we do multiple iterations. Okay, but then what I can do is I can apply, because this is nonlinear, I can apply one of the solution to nonlinear algebraic equations problem. So I can apply, let us say, the secant method that we have learned to solve for this problem. Okay, Let us apply the secant method. What does secant method do? Secant method is basically going to draw a secant, right, between these 2 points. So it's going to basically draw a secant. That is a secant. Okay. And then we say that this function is crudely approximated by the secant. So I can calculate the zeros of the secant. That is going to give me a root that is very close to the value that the function produces. And I'm going to basically repeat the same thing, do this multiple times. Okay. That means what will be the equation of the secant? The equation of the secant we can write as this. So equation of the secant would be essentially y prime of 0. That means that is on the what is on the x-axis. Okay. So this is my independent quantity. So you can think of y prime of 0 like some x. So I want to write what is y equal to mx plus c, or I want to write what is x equal to my plus d. Okay. So y prime of 0 is my x equal to, so I can say y2 prime of 0, that is this quantity, right? That is the intercept. And then I have some slope or inverse of slope of this secant, okay, times what I have here. Essentially that is going to be y of L, okay, that is my y minus y2 of L, okay. So what is y of L here? So y prime of 0 is like something like my something like x, okay, and yl is my something like y, okay, because this is on the y-axis, okay. That's what we have. And then y2 prime and y2l are the intercepts, right? y2 prime 0 is here and y2l is here. Okay, these are the intercepts. And m is the reciprocal. M is the reciprocal of the slope of the line or secant. It is reciprocal because we are writing x in terms of y. So if I had written y in terms of x, m would have been the slope. Okay. So now it is the reciprocal of the slope, and then m value is nothing but x2 minus x1 by y2 minus y1. Okay. So I can write what is my, I think it's better to write here. So m is going to be y2 prime 0 minus y1 prime 0 divided by y2 of L minus y1 of L. What does this mean? This is nothing but your y2 prime 0 minus y1 prime 0 divided by y2 of L minus y1 of L. This is basically something like y2 minus y1 by x2 minus x1. But then we are looking at inverse of the slope. So it is basically x2 minus x1 by y2 minus y1. Okay, so that is what I have. So that is my value of m. So it means with this slope, I am able to construct. That means I know what is the slope because I have already guessed y1 prime 0, y2 prime 0, and I have integrated and calculated y1L, y2L. So I know all these 4 values. I can calculate the slope. Once I know the slope, I can put in, and then I know this equation. Now the equation of the secant I know because I know what is y2 prime 0, what is y2L. Y of L is just y, y prime 0 is just x, and then slope I know, right? So equation of the secant we know. Then how do I choose what would be the next guess value for y prime, right? Because we know y1 prime, y2 prime. We want to pick what is the y3 prime 0, right? This is the question. What is the next guess? Y3 prime 0 would be how much, right? So y3 prime how would be? We are already given what is y sub L. That is the value of y at x equal to L. We are already given that value. Let us say that value lies somewhere here. Let us say that is YL. So from YL, we're going to basically draw a line that cuts the secant, right? Okay, so that is the secant, and it is intersecting somewhere here. Then I'm going to draw, extend this line, and then see where it is intersecting. Okay, that is basically going to give me what is my y3 prime of 0. That means how do I get y3 prime of 0? I'm going to substitute for y of L equals y sub L in the equation for the secant. That means in this equation, I'm going to substitute for what is for y of L. I'm going to substitute y sub L. That is going to basically give me this problem, and then calculate what is y30 from here. Okay, that means I go to this equation. Okay, so let me rewrite these equations. Okay, so this is y prime 0 equals y2 prime 0 plus m times y of L times y2 of L. Okay, and then my m was y2 prime of 0 minus y1 prime of 0 divided by y2 of L minus y1 of L. Okay. Okay. Let me now substitute for, instead of this y of L, I'm going to substitute for y sub L. That is the boundary condition that is given on the other side. Okay. I'm going to substitute for that with a hope to calculate what is y3 prime 0. Okay. So if I substitute that, that is nothing but where the secant is intersecting this line. That is going to give me y3 prime of 0. y3 prime of 0 equals y2 prime of 0 plus m times y sub L minus y2 of L. Okay. So that is my y3 prime of 0. So I have obtained what is y3 prime of 0, which is the next guess value. So once I have the y3 prime of 0, I can again integrate, right? This is the new guess value, which I obtained from two initial guesses I had. That means I know what is y3 of 0. y3 of 0 is y0 and then y3 prime 0. So I can integrate these two using my RK2, RK4 and calculate what is y3 of x, right? Essentially, that is something like this. That is y3 of x using the function, right? So that means when I solve for this again using the function, my y3 of x is going to basically y3 of L, right? So from the y3 of x, I can calculate what is y3 of L. That is going to be y3 at x equal to L. That value is nothing but it's going to be the intersection where it is going to intersect with this function, right? That is my y3L, right? So that is the value for my y3 of L. Okay. So we obtained this value. Then what are we going to do? We are essentially going to again draw a secant between this y2 and y3. Okay, I can use a different color. And then once you have this value, then again I'm going to draw, evaluate this secant at y of L. That's going to give me what is y4 prime of 0. Then I'm going to get what would be, the next y4 of L. That is going to be y4 of L. And then I'm going to draw another secant and so on. Okay, I proceed. I mean, essentially, you know that your solution is somewhere here, wherever this y of L cuts the the nonlinear function. But then the nonlinear function we cannot solve. That's why we are using this iterative approach to eventually converge to that iteration. And once you have converged, you know that is your correct y prime. Let us say if it converged after n step, that is your yn prime 0. If you had used that, you would get this corresponding y of L to a pretty close proximity. Okay, so that is the idea. Okay, is this algorithm clear before I write down the steps? Is it clear? Any questions? This is a little bit tricky, but I think if you followed me, I think it is straightforward. Questions on this?
Sir, I have a question.
Yeah.
Sir, is it a necessity that y of L should be bounded between the two guesses?
Need not be. Just like think of the root finding method, the secant method. It can be on other sides also. It will converge to eventually it will come back here.
Okay, sir.
Yeah, just like the root finding. You're doing root finding here. What is the root you're talking about? Your root you're talking about is where does your function, this blue line, is cutting this y of L. That is your root. That is what you want to calculate. Earlier, you were trying to calculate where does the function change its, where does it cut at the x-axis. Now you are trying to look at where does it cut y of L. Y equals y of L. That's all. Instead of the x-axis. So it's basically, it need not be bounded. So y of L need not be bracketing or y1L and y2L need not be bracketing yL.
Understood, sir.
Yeah. Any other questions, anybody? No? Okay, fine. That means in general, we can write an iterative algorithm. The iterative algorithm is basically, so inspired by this statement, we can write an iterative algorithm, which is y alpha 1 plus 1 prime 0 equals y alpha prime plus some m alpha minus 1 yl minus y alpha minus 1l. Okay, so that is my algorithm, iterative algorithm, where m alpha minus 1 is going to be given as here y2 prime minus y1 prime. That's going to be y alpha prime minus y alpha minus 1 prime divided by y alpha L minus y alpha minus 1L. Okay, that's what we have here. Okay, so if I do this for several values of alpha, eventually my y of L that I would obtain here will get close to YL. Then we are going to stop iterations. We're going to stop iterating. Okay, then we would have obtained what is y alpha plus 1 prime 0. Then using which you can already calculate what is the y as a function of x. Correct. That means we found what is the correct guess value, which would give you the correct y of x, right? So that is the idea. So this is more like an indirect method, but I think it's a clever method, in which you're trying to calculate what you want in order to make your existing algorithm work, right? Yeah. Okay. Now, of course, again, the convergence of the secant method will depend on how steep this curve is. That means how strong is the nonlinearity? Strong is the nonlinearity between y prime 0 and YL. Okay, so based on that, the convergence of the secant method will depend. It may converge or it may not converge, so that all will depend. But then, of course, you have to make adjustments to make it work, maybe. Okay. Any other questions? Anybody? Okay.
No, sir.
Yeah. Go ahead.
No, sir. Like we'll review and get back to this one.
Okay. Fine. All right. Okay. Then let's move on to, so for example, the in general, like if you pick up any fluid mechanics book, the Blasius solution is typically solved using shooting method. Okay. So we have already written this thing. This is f double prime plus 1/2 f prime equal to 0. Okay, so that is the equation you would get. This is basically a non-linear ordinary differential equation. So you can apply whatever your RK4, RK2 to solve this problem. Okay, typically in this you would know for the conditions for f, what are the conditions for f. Essentially what is the velocity, what is u. Typically you will know what is u at x equal to 0 is 0. That is what is known. You will also know what is u prime at x equal to 0. Okay, so this is also known. No, not 0. This is some value. Okay, some slope. So here I think derivative of f will be equal to u. Okay, so that is the idea. And then you will also know what is u double prime, or so essentially this is already f prime. So integration of this also you need one condition. What is f of 0 is one condition, and then f prime and then f double prime. So with this you will be able to solve this as an initial value problem and then obtain the velocity profile. Okay, so that is an example of where shooting method was typically used, and then it is also used in heat transfer when you want to solve for the temperature profile for this flow or a flat plate kind of scenario. Okay, where you have a forced convection heat transfer. So there also this shooting method can be applied. Okay, so that is one example. So now let us move on to the direct method. Okay, so the direct method is actually, as the name suggests, it is actually very direct, and also it is very straightforward to solve for a boundary value problem. So this is a straightforward method, especially in the light of the shooting method. You will find direct method to be very easy, So essentially what happens is you have this general second order ordinary differential equation, that is y double prime x plus a of x times y prime x plus b of x times y of x equals f of x, right? So this is what you have, and then you're given boundary condition. So let us say you have a domain which is going from I equals 0 to I equals n, okay, and then you have I equals 1, 2, all the way to n minus 1. So I equals 0, I equals 0 and I equals n are the boundary conditions that are given to you, and then everything else in between, these are all the unknowns you have to calculate. Okay, so these are all the interior values that you have to calculate. Fine. Then what you do is that you are going to essentially choose some pitch as your step size, and then directly apply your final difference. You're going to apply the final difference approximations that we have already learned for your y double prime x and then y prime x, and you're going to substitute them in this equation and then form a system of linear equations. Okay, that means you're going to basically get eventually some ax equal to b, which needs to be solved. Okay, so that is the direct method. I'll discuss this direct method for a particular second order central differencing of the second derivative and the first derivative, maybe in the tomorrow's lecture. Okay, so with that, by tomorrow, I think we'll finish the chapter on the ordinary differential equations. We will then tomorrow itself we'll be able to begin the last and final chapter, that is the solution to partial differential equations. Okay, so the agenda for tomorrow is finish this direct method for boundary value problems and then look at the solution to system of solution to partial differential equations. Okay, so that is for tomorrow. Okay, I'm going to stop here, and if you have any questions, feel free to ask me.
Hello.
Hello, yeah.
Sir, for this second method, had
Yeah.
that function been some parabolic function? So would the solution still converge or some other method we need to?
No, if it is parabolic, it's basically quadratic, right? It's basically quadratic.
Yeah, yes.
Yeah, I mean, unless you're not going to get into slope of infinity, right? If this goes to infinity, then you will have trouble, right? So unless it is not going there, this will still work. I mean, essentially the same limitations that we have learned for tangent method, secant method apply here also. Yeah, but hopefully it will run. If there are no not so well behaved functions, then it will not run. But otherwise, if it is well behaved, then it's going to work properly.
Yeah, means here itself, if we take this blue curve mirror image about this red, and if we have some curve like this, so will it still converge? That was the.
You mean to say something like that?
Yes.
Yeah, I think it will work. I mean, so essentially, then in that case, you will have here and here, right? In that case, this is going to be the line, and this is what you will calculate, and so on, right? So your root is here instead of there. So you're going to converge this way.
Okay.
Yeah. I think you can think about it. If I think it will converge, not a problem. Any other questions, anybody? Okay, if no questions, I'll stop here. I'll see you guys tomorrow at 4 o'clock. Okay. All right.
Thank you, sir.
Thank you, sir.
Thank you, guys.
Thank you,
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Several participants left the meeting.